So now we're going to change topics a little bit, and we're going to talk about another type of reaction that occurs with a conjugated diene. And this is going to be a reaction that we're going to do in the lab. I believe it's lab 11, reaction of a conjugated diene with eucalyptus oil. And so we're going to be doing the Diels-Alder then. This is the reaction, this reaction of a conjugated diene is not like the conjugated diene reactions we've been covering, where we have a 1,2 and a 1,4 addition product. This product is always going to form a 6-membered ring, and it's called a Diels-Alder product. So it always forms a 6-membered ring, and we have a conjugated diene plus another, let's say a monoene, just an alkene with 1 pi bond. And these two products react to form the 6-membered ring. And what happens is that we would have the pi bond in the molecule shown is actually, if we number our carbons, then our carbons are as follows. That the pi bond always ends up between carbons 3 and 4. Okay, so at least you can confirm the pi bond will always be between, no, that's not correct. That's not right. Okay, so carbon 1 binds to carbon 5. Yes. So what we would have, 1, 2, 3, 4, here, this comes down there. Yes. Okay, my mistake. The pi bond is always going to end up between carbons 2 and 3. Which was what I originally thought. I just numbered the ring incorrectly. Oh. So I'll just renumber this. And I'll call this carbon 5 and this carbon 6. So we have 5 and 6. Okay? And the position in 5 and 6 can change, but the position of the pi bond will not change. It will always end up between carbons 2 and 3 of the diene. All right, so then we can look at the mechanism for this reaction. The mechanism, one of the pi electrons of the diene are donated to the dienophile. Then the pi electrons of the dienophile are donated to the other terminus of the diene, and the pi electrons at that between C3 and C4 have to move to between carbons 2 and 3. Okay? So that gives us our transition state showing where all of our new bonds are forming or breaking. So here we have the pi electrons that broke here and here and here, and our new bonds forming from the dienophile to the diene, and the new pi bond being added between carbons 2 and 3. So we have a new sigma bond, and a new pi bond. This type of reaction is called a pericyclic reaction. It's a cyclic shift of electrons without moving carbons. And more precisely, we would call this reaction a 4+2 cycloaddition. So we have 4 pi electrons plus 2 pi electrons to make a 6-membered ring. So we can go over it again. We have numbered our diene 1 through 4. Carbon 1, the pi electrons between carbon 1 and 2 bond to the electrophile of the dienophile. Then the pi electrons of the dienophile, which is always the molecule with 1 pi bond, are donated to carbon 4 of the diene, and then the electrons between carbons 3 and 4, the pi electrons there, move to the position of between 2 and 3. So here we have a 1,4 addition reaction, and it's to form a cyclic product. So Diels-Alder is always a 1,4 addition. We have to consider how groups are going to affect the addition. And if our dienophile contains an electron withdrawing group, then it will be a more reactive electrophile. So our dienophile is always our electrophile in the first reaction for Diels-Alder. And its electrophilicity can be increased by adding what we call electron withdrawing groups. Okay, so an electron withdrawing group is a group that can accept a lone pair or a pair of electrons. An electron withdrawing group is a group that where resonance allows us to move electrons onto an atom. So a C double bond O is an electron withdrawing group, and all electron withdrawing groups are going to have an sp2 atom. They have resonance. So our electron withdrawing group here is our C double bond O. Our pi electrons of our dienophile can be moved from the 2 carbons to between the carbon with the to this position where we have to move the pi electrons of the carbonyl group to the oxygen. And then we have a resonance structure, you see, with a positive charge at this terminal carbon and a negative charge on the oxygen. What that means is that our diene is going to bond at this positive carbon first, because this is the most positive carbon in the molecule. So our electron withdrawing groups are going to make our electrophile more attractive, and it's going to make this carbon more positive, so that our dienophile bonds at that carbon before the other carbon. So the dienophile will bond to the carbon that is furthest from an electron withdrawing group or an electronegative atom. Examples of Diels-Alder reactions, we can do a reaction with, for example, maleic anhydride. And make a derivative. And so it doesn't have to be it can be any alkene. As long as there's 1 carbon-carbon pi bond, it can be a dienophile. And even an alkyne can be a dienophile. It doesn't matter if it has 2 pi bonds between the same 2 carbons, as long as it's not a diene and it has 1 pi bond within the molecule. So maleic anhydride is symmetric, and so it doesn't matter which carbon I bond to first because of that. So I can draw my arrow to this side of maleic anhydride, then to the end of this carbon, and then move those electrons there, so that the new bonds that I'm forming are here, here, and then I move my pi electrons here. So that would make this 1, 2, 3, 4, the carbons of the diene, and then you can see the position of the original maleic anhydride dienophile. For our alkyne, we have a CO2CH3 group. If you draw that out, that should be C double bond O, single bond O, CH3. And then we have our C triple bond C to CH. Now this is the electron withdrawing group, what we call EWG, electron withdrawing group. And the pi carbon that is furthest from the electron withdrawing group is the most positive. So that would make the terminal alkyne carbon the most positive. And that is where carbon 1 of the diene will bond first. So if I switch to green arrow, or I don't know, what color did I pick? Yeah, green, okay. I'm gonna have label my diene 1 through 4 like this, and have carbon 4 bond to that most positive carbon. Then my 1 set of pi electrons from the triple bond moves to make a bond at carbon 4, and then the pi electrons between carbons 3 and 4 are going to move to between carbons 2 and 3. So that would give us our carbons as 1, 2, 3, 4 in our product. Notice that we still have 1 pi bond that is untouched because I only used 1 set of pi electrons from the alkyne. And I'll circle the new bonds. The new sigma bonds are here and here. And then, of course, we had the new pi between carbons 2 and 3. There is a worksheet that I can give you for Diels-Alder. It will be really good practice. And you'll notice that once you start to practice the Diels-Alder, because of the repetition of the movement of the electrons, even though you're working usually with a different diene and a different dienophile in each case, you'll get used to the way that the reaction occurs and you'll become more of an expert with this reaction. And I usually find that the Diels-Alder reaction is one of the reactions that students do not struggle with very much, as long as they practice. So the reason that the Diels-Alder reaction occurs is the alignment of molecular orbitals. So we have either that the dienophile's lowest unoccupied molecular orbital reacts with the diene's highest occupied molecular orbital. And what happens is that when electrons are transferred between the HOMO and the LUMO, the carbons that the electrons are transferred to must be in phase. So blue goes to blue and green goes to green in phase. And what they're saying is that, well, in some cases, the dienophile may be the nucleophile, but in that case, the HOMO, the highest occupied molecular orbital, donates electrons to the LUMO of the diene, and still we must have in-phase overlap of the orbitals to form the new bonds. Okay. That's not something that you are going to be asked about on an exam, but it is a good thing just to try and understand how the two orbitals are adding together to make the new bonds. Okay. What if both reactants are not symmetric? Then we have to find the most nucleophilic carbon and the most electrophilic carbon. Okay, so if you look at these two reactions, it's assumed that two products are possible, right? And what they're moving is not the dienophile, because we already determined that when we have an electron withdrawing group, the most positive carbon is the one that is furthest from the electronegative atom. What we've done instead is we've added the dienophile from both positions. Okay. Now, an OCH3 group or an sp3 carbon with two lone pairs is considered an electron donating group, or EDG. Electron donating group. And it's sp3 hybridized, so it can't withdraw electrons to it. It can't accept a pair of electrons, but what it can do is it can donate a pair of electrons. Okay, and if it can donate a pair of electrons, then we can have a resonance structure where we have a formal negative charge on that terminal carbon atom through electron pair donation, because now it has a lone pair sitting there. And this is one of the resonance forms. Okay, so that's our resonance structure. So what that tells me is that the most negative carbon of my diene, in this case, is this last carbon here. And so it should make sense to you that the most negative carbon is going to bond of the most negative carbon of the nucleophile will bond to the most positive carbon of the electrophile. So that the first set is going to produce the correct product, and the second set would not. And we can look at this. Your book also is looking at this. So donating electrons by resonance, the methoxy group, is making this carbon more negative, and the resonance structure for the dienophile makes its terminal carbon more positive. And so the actual product that forms is to have the most negative carbon of the diene bond to the most positive carbon of the dienophile. So that when we perform this Diels-Alder reaction, we do not obtain this product, we obtain this product. And we can draw our electron arrows for the reaction mechanism. so that we have C1 bonding to the carbon I've labeled as 5, the carbon labeled as 6, the pi electrons of 5 and 6 bonding at carbon 4. Really, it should come from the pi bond. So from this pi bond to carbon 5, from the pi bond between 5 and 6 to carbon 4, and the pi electrons of carbon 3 and 4 going to carbons 2 and 3. And that gives us our final product. Let's draw the new bonds in red. The new sigma bonds I'm going to draw in red. Okay, and we still have our carbonyl group, and we still have our methoxy group. And then we have our pi electrons that move to between carbons 2 and 3. And if it helps, I can label the carbons as I numbered them when I was determining the reaction. So 1, 2, 3, 4, 5, and 6. And notice that this gives us our final product here. Okay, this is more about Diels-Alder, and I will come back on Diels-Alder on the next video so that we're not getting the videos too long.